Hi.
Hello,
So, how are you?
I'm good. Yeah, what about you?
I'm all good. How about you were on a holiday? No, you had some test, right?
Yeah, yeah.
How-
It was pretty good. Yeah, it was seven. So
Okay. That's nice. So, I think we had left the photoelectric effect in between, if you recall, or the
yeah,
quantum physics in between. So, we can continue from there. Is that okay?
yeah, that's fun.
Presently, what is going on in the school?
Right now there is IAs. The final IA is due in about a week, and some other IAs as well.
Hmm.
Um, yeah, mostly just tests
So,
and stuff.
okay, were you able to add the content that was required in the IA?
Yeah.
That's nice. Okay. So if you recall, what is this photoelectric effect? Any idea?
Um, it was something. It was with when photo.
Mhm. Photoelectric effect.
Yeah. When like the emissions um uh it's like the effects from the emissions when there's radiation, something along those lines, I think.
Okay, maybe I can to remember the best. I can give an example. The
Yeah.
solar cells. You know what is the solar cell? What does it do?
Solar cells. Not
Photovoltaic
sure.
cell. Um,
uh
you see certain calculators, they work on the light that falls on it,
oh, yeah, yeah.
right? So what happens when the light falls on the solar cell? What does the solar cell do?
It turns that into energy, charge.
So that is what it produces electricity.
Yeah.
So that means a solar cell is converting your solar energy into electric energy. This
Yeah.
is what we are going to learn. Okay. So here, basically, if you see the light or any kind of electromagnetic radiation that falls on a metallic surface will cause the electrons to be emitted from the surface. And the electrons are
Okay.
collected and then the electrons pass or move about and that gives an electric current.
Okay.
So basically, photoelectric effect is producing electricity using photons. Now, what does photo? Photo means light, right?
Yeah.
How does it relate to quantum? If you can just kind of, last time I had said about quantum. I mean, how does it even concern or connect to photoelectric effect?
With like the with lights with as in particles, considering light with particles, and then you can consider it as like quantities, like really small, a bunch of photons, and and you can quantize that.
Hmm.
to-
Hmm. Absolutely right. So this means that you are able to quantize light, which was considered to be a wave. Okay. So
Mhm.
initially it was thought that light is a wave. Okay. And why? Because it successfully explained the processes like interference, diffraction, reflection, or refraction. Okay. All these were successfully explained, even for that matter, polarization. Okay. So basically, all these, we can say that all these are wave phenomena. However, when it came to photoelectric effect, now what happens? What is the problem?
I couldn't really explain it.
Huh. This wave model failed. Okay. This wave model failed over here. So now what was the alternative?
That light could be particles as well.
So who said that?
Einstein.
Uh, Einstein, the big chap. He said that for light is made of particles. And these are not mass particles, these are virtual particles. Virtual particles in the sense, virtually, practically zero mass. Okay. And
Okay.
these are particles or these are virtual particles. Um, or packets of energy called as
Photons.
yes, quanta. Quantum means a packet. So a quanta of energy is called as photon. So therefore, you have this photon coming up over here. Okay. Now,
Okay.
what is the, what do you know about this photon? The photon that we are talking about, it has certain energy, right?
Yeah.
Any idea?
Was it I remember reading about it as well.
Mhm. We have E equal to mc square. Is that?
Oh, yeah.
Uh,
Yeah.
okay. Not really. It is E equal to mc square is Einstein's equation, energy mass equation. Here it is going to be
Mhm.
Planck's equation. Planck's equation is E is equal to H.
Oh, H,
What is H?
Planck's constant.
Value?
What value? Oh,
You're not expected
I
to know.
yeah, I see. Yeah, over here, 6.63 times 10 to the negative 34
Times 10 to the minus 34 unit. Very important unit.
joules second.
Why this is very important, you will know very soon. Okay. So this is it. And what is the F stands for?
The frequency of.
Frequency of the related wave.
Yeah.
Okay.
Okay.
So this is it. Now the thing is that photoelectric effect was explained by the particle model, and the rest is the wave model. So how is that? We can come to a conclusion that sometimes the light behaves like a wave, and sometimes it behaves like a particle. Or together
Okay.
we can call this as what nature? It is the
Uh, duality of nature. The
dual nature of
dual nature.
dual
Yeah.
nature of light. Okay. It's not about light, it is all the electromagnetic radiations, EM waves.
Yeah.
Okay. Now, I need to give one definition that's important. That is, what is 1 electron volt? One,
1 electron volt. In terms of like coulombs or
basically, what is this? Is it a unit for charge or voltage, or is it a unit for energy, or what is that electron volt? Is it mass,
charge, I think.
charge? Mhm.
Yeah.
Okay, give the formula for voltage.
V equals IR
Not that
for the for the
definition.
um
Voltage is defined
voltage
as
the hmm, oh the
work
power over charge work done over charge, yeah.
work
Okay, I see.
charge. Recall, because primarily when
Yeah.
you find current, current is nothing but charge flowing per unit time. Okay, and voltage is work done per unit charge. Because it's between 2 points, it's the work done in taking the charge from one point to the other. Okay, so this will be
Okay.
because now you see, if I am taking this equation, V is equal to W by Q, can I not write W is equal to VQ?
Yeah.
So Q, if it is an electron, it becomes E. Q becomes E if it's an electron, and then volt. So don't you think electron volt is a unit of work done, or rather energy?
Yeah.
Okay. So the smallest unit of energy is electron volt. It's not joules, because joules is a very large value. So 1 electron volt of energy is equal to how many joules?
Was it like the 1.66
Mhm.
1.60 times 10 to the
Correct.
negative
Yes.
19?
Yes, absolutely. How do you do it? We'll just replace this, okay? So 1
Yeah.
electron volt can be written as 1 into E is charge, 1.6 into 10 to the power minus 19. What is the unit? Coulomb. And volt, 1 volt is again volt. You see, its
Yeah.
unit comes here and CV. You know what is CV? Coulomb volt is nothing but joules.
Yeah. Okay.
This is Coulomb, this is voltage, this is joules. Okay, so I can replace this as 1.6 into 10 to the power minus 19 joules is 1 EV.
Okay.
At the same time, 1 joule should be equal to how many EVs? How many electron volt?
1 over 1.6 times 10
1
all that.
over 1.6 into 10 to the power minus 19. Okay, so 1 joule is equal to 1 over this much. Otherwise, you can say 1 electron volt is these many joules. Per electron volt, you have these many joules. Okay. Now,
Okay.
by definition, what is the definition of electron volt?
Definition.
It is the amount of energy, if you recall.
Amount of from 1 electron to
One
work
electron,
done.
take 1 electron, take 1 volt, correct?
Yeah.
Take 1 electron, take 1 volt. That is, you're providing a voltage of, okay, as if you're connected to a battery and like this, and it's an evacuated chamber. And this is 1 volt. And you're placing an electron just here. Okay. Electron is negatively charged. Automatically, this positive is going to attract. Correct?
Yeah.
I hope you're following.
Yeah.
So you're accelerating the electron through how much voltage?
V, the potential difference between
1 volt. Here it is.
yeah, 1 volt. Oh, okay, 1 volt.
So if you're accelerating through this much, it gains an energy of 1 electron volt. This is
Okay.
1 electron volt is the energy gained when and 1 electron. Okay, an electron is accelerated through 1 volt. Clear?
Yeah.
All right. Now, if I say that I'm accelerating an electron through 5 volts, so 5 volts give you how many EV of energy for the electron?
5 EV.
5 electron volt. If an alpha particle is accelerated through 1 volt, how much of energy does it gain?
4.
What is the charge of alpha?
No. Was it 4 times? Was I thinking about the mass? Alpha was
Alpha is a helium nuclei,
2.
2 protons. So
Yeah,
therefore,
2.
if you accelerate through 1 volt, how much of energy does it gain?
2.
2 electron volt. If you accelerate
Yeah.
an alpha particle through 5 volt, it gains an energy of
Alpha particle 10.
10. If you accelerate a proton rather through 1 volt, how much does it gain?
A proton to 1 volt. Same. Yeah, 1 electron volt as well.
Because the charge of proton is also E. It's not any different. Mass
Yeah.
doesn't matter over here. Clear? So now you know
Yeah.
the schedule. So always remember while you're doing equations, okay? See this formula. You have E is equal to HF, right? E
Yeah.
is equal to HF. Now, this unit of H is what? Joule second. And suppose if I give you energy in electron volt, please be careful to convert it completely into joule or convert it completely into electron volt. You will go wrong if you do not convert. Got it?
Okay.
Because this is
Yeah.
in joule. It's not in electron volt. Okay. And frequency is, of course, per second, means hertz. You see seconds, joule seconds per second. I hope you're able to,
Okay.
right?
Yeah.
Okay. So now you have understood where we are going, and we'll look at photoelectric effect. I hope the board is okay.
Yeah, yeah, it's fine.
I'm still kind of adjusting with this thing. So it's not catching up entirely. Like probably I'll have to be a little slow to, let it paste or get printed. Okay.
Yeah.
Now we know the photoelectric effect. Maybe if you know something, you can tell me. Okay. Photoelectric. You can also annotate, right?
Oh yeah.
Okay.
Oh, I can.
Because you're moving around behind.
I see.
So you can. So anyways, photoelectric effect is an effect. What happens when a radiation falls on a metallic photosensitive surface? The surface will emit electrons. That's it. Okay.
Okay.
If you have a photosensitive surface, and if there is a radiation falling on this, okay, radiation coming and falling on this, then this surface has electrons, atoms with electrons. The electrons gain that energy and leave the surface. And this electron is captured by a particular, anode or collector, and then you have the photo current. Clear? Can
Okay.
you tell me what is the photoelectric effect?
Photoelectric effect is when photon is incident on like a metal. That way, what type of metal did it have to be again? Some was it specific or did it not matter?
Hmm. You tell.
Okay.
What is
It's when it's incident on like a metallic surface, and then electrons will be emitted from the surface.
it's a photosensitive surface. Okay.
Photosensitive. Okay. Yeah.
So that means any radiation. The radiations can be UV radiations, it can be stronger X-ray radiations, or it can be, ultraviolet, indigo, blue, green, or visible light, or even infrared radiations. Okay, depending on that, you will have the sensitive surface also. You know which surface is sensitive to which radiations, you will have to take that. Okay.
Okay.
All right. Now let's take the diagram. That is, you're going to do this experiment, whatever is the setup, it is in a evacuated chamber. So this is the evacuated chamber. Okay. There is a photosensitive surface over here. And there should be some window over here, right? Some glass window, quartz window or something. And these are, you will have a collector over here. This is, which collects the electrons. The collector can be positive or negative. We will be changing. This is a variable voltage for that reason. Because sometimes we will do positive, sometimes we'll do negative, and we will analyze everything that is happening. Clear? This is a variable voltage. Variable means not only vary in the value, it will also vary in the polarity. Like presently it is positive, right? I can make it negative and do my testing.
Okay.
So, okay, now to understand photoelectric effect, you have to, strike radiations. The incoming radiations are striking the surface of a particular frequency, okay? And on the surface, you can see, on the surface, there are atoms, nuclei, and the electrons, okay? The electrons, what they do, they capture one photon each. Electron captures one photon each and then leaves. So, if this is one photon, it will capture and leave. One photon, it will capture and leave. That means the surface is getting ionized and the electron is leaving. Electron is gaining the energy from the incident photon. Incident photon has energy of E is equal to HF, correct?
Yeah.
Okay. So these electrons leave the surface. Now the thing is that these electrons do not have a specific kinetic energy. Some electrons will come till here. Some electrons will move little forward. Some more electrons can move little forward, or some can be just at the surface. or some can just reach over here also. So the kinetic energies of electrons are not specifically, same for all of them. Why? The
Oh,
reason is very obvious. Maybe you can tell me why.
um, uh, very obvious.
Huh. Look at this. The atom can have some more electrons. The inner electrons are tightly bound. So
Yeah.
electrons have to fight with that and lose more energy and come out. The outer electrons are easily they can leave and come out. They don't lose much energy, right?
Oh,
So,
yeah.
get what I'm trying to say?
I think, yeah.
Tell me why the kinetic energies are different for uh,
The electrons that are more like the outer, as you said, will have an easier time leaving the surface, and so they'll lose less energy, while the ones that are more inside will lose more energy from trying to get out, trying to leave.
okay. So this is understood. So that's why it is. But then you have a collector. So this is a collector plate. What does the collector do? It collects all of them,
Yeah.
positive. So then you have the photocurrent. Okay. All the electrons are going to the right. And obviously your current will be to the, conventional current is opposite to the flow of the electrons. Okay. And
Yeah.
electrons are flowing to the right. All right. Now,
Okay.
okay. This is the thing. There are some things that we have to figure out. That is how exactly, you know, how exactly we can set the equation of the energy. That is, the incoming energy is E equal to HF. A part of it is lost in the atom to, get free of the atom, right? And then the remaining is
Yeah.
its energy. So what are the things? An incoming energy, out of that, a part of it is lost in overcoming the force of attraction of the atom. And then the remaining is its kinetic energy, correct?
Yeah.
Okay. So I can say that your incoming energy, so suppose that, I'll just show it here. Suppose that this is the photon, the incoming photon has an energy of 7 electron volt. And the atom itself needs, say, 2 electron volt. So how much will be the EK? EK of the electron will be how much?
Uh, what was the original one? 7 volt, right? Okay, five.
Photon
5?
has, yes, the photon has 7 electron volt. The atom takes away 2 electron volts. The remaining kinetic energy is 5 electron volt. You're happy because
Yeah.
it's some. Okay. So, but it's not that straightforward. Let's see. This is basically, we will have to define one thing called as work function. Okay. What is work function? This is now another term. Okay. So work function, this is of a surface. Work function, phi of the photo surface.
Okay.
Okay. So what is the work function of a given surface? It is the minimum energy required for photoelectric effect to take place. Oh my, I can't write P. Photoelectric effect. Sorry.
Yeah.
I didn't expect this to come out. uh, Sometimes unguarded, I should have thought. So, okay. Okay. So what is work function? It's a minimum energy required for the photoelectric effect to take place.
Okay.
Okay. So just to start, otherwise it will not happen. You have to give that minimum energy. So let us look at the surface for that matter. I think today's meeting will be 45 minutes and then we'll rejoin again because I'm using this new thing. So the meeting will get ended. We just rejoin the same thing. Okay, once it gets ended.
Okay.
Okay. I'll just draw the potential well of an atom. Okay. The surface, you see this photo surface has atom. Okay. So this is the atom and this is the potential well. In the sense, this is suppose the electron at the outermost level. Okay. And that means it has a potential energy of this negative value. The atom is holding it in a well. If you want to free it, you have to give this much of energy, isn't it? If you want to free this, you have to give this much of energy, if I'm right.
Yeah.
Hmm? So,
Yeah.
so this is the work function. Work function is defined for the surface electron, not for the electrons which are at the bottom. Bottom in the sense in the inner shells.
Yeah.
For the electrons which are in the inner shells, we have no idea how much they will lose. Okay. So what we define, all our equations, our photoelectric effect equation is meant for the surface electron.
Okay.
Getting it? So
Yeah.
work function is the minimum energy required for the photoelectric effect to take place. Means removing the easiest electron. That means just start the photoelectric effect. Don't worry about the other electron, just start it. It is
Okay.
possible to start if you can just remove the easiest one, right?
Yeah.
So this is when you provide an energy just required. Okay. Suppose you're giving an energy which is just required. So I think I'll make little better. The reason being that you're giving the least energy. So the wavelength has to be small or large,
Large.
isn't it? So
Yeah.
this is the way we represent, although we say that it's not a wave, okay, it's a photon, but how do we represent? So we know that
Mm.
ultimately even a photon is related to its wave, okay? So lesser energy we are providing right now, we are just giving the least amount of energy required, okay?
Okay.
This is the least amount of energy that you're providing, and the electron which is just there on the surface, okay? This will just free itself and sit right here.
Okay.
Okay, so this is H F naught because that's a minimum energy E naught that you are giving. Okay.
So to actually get it to the collector plate, you'd need like probably some more energy than the
Yeah, on
work
its
function.
own, yes,
Okay.
on the own needs more energy. Otherwise, it'll come out and it's there out, but the photoelectric effect has started, no doubt. Okay, but now it's not reaching the collector is another point. That's not.
Okay.
So you have started photoelectric effect with a minimum energy that's called as the work function of the metal surface. But that's also equal to the energy that you provide. E is equal to HF naught, the minimum. Okay.
Okay.
Let's provide a little more energy. Okay. So, and remember, work function is concerned with only, they will not say, but you better know, it's only the outermost electrons. Only outermost electrons. Why? Because the inner ones, we have no idea how much energy is extra required. And we are concerned
Yeah.
with starting the photoelectric effect. Now let's take another one, a situation wherein now I have the same well and this is it. Okay. And this is the electron, which is topmost. There will be electrons at the bottom also, like bottom in the sense they are at a lower, more potential energy is needed, or sorry, more energy is needed to remove it out. Okay. So now if the incident photon is having more energy, okay, E is equal to HF. Now what will happen? It will lose phi energy. The work function is the energy required to free itself. So not only that, but it will come out with just. So it's not only that, it will come out with what? Tell me, maybe you can say.
Like more like
It will
the
come
excess with
more kinetic energy, right?
yeah.
So this is EK, kinetic energy. That means, how is the equation going to be? Can you formulate now?
That the EK is the E minus 5.
Very good. So EK is E minus 5, or can I write the other way around? E is equal to 5 plus EK. E input,
Okay.
incoming, this one. But now, if I ask you in any kind of photoelectric effect, what is the maximum kinetic energy? Which electron is going to have the maximum kinetic energy?
Sorry, could you say that again?
In a photoelectric effect, which electron is going to have the maximum kinetic energy? The inner one
The
or the outer ones?
outer
Outer.
outer ones?
So exactly, this is not EK, but it is EK max. Do you agree?
Okay. Yeah.
The rest of them will be, okay? So this equation is meant for EK max because you're concerned with phi. You're not talking about the energy lost over here. You're not talking about the energy lost over here. No. You're only talking about the phi, right? Do you agree?
Yes. Yeah.
Okay. So now our Einstein's equation is this only. That I'll just write it again. That is E is equal to HF is equal to phi plus EK max. This is the Einstein's equation.
Okay.
Now, if you look at the same thing, just suppose that I'm giving, okay, let the same energy fall on this. Can you see the internal electron? Okay. The same
Yeah.
electron, I mean, the radiation is falling on this also. Okay. So when it is falling on this, will it have EK max or it'll have little lesser energy?
Oh yeah, less.
Less, because it's losing some extra energy to come to the top of the surface and then again. So it'll have an energy which is EK, not EK max.
And can that be calculated as well, or is it no?
We are
Okay.
not interested in the kinetic energy of the inner electrons. All that we are doing is in the entire this thing, we are concerned with EK max. And EK max is related to the electron which is on the topmost level. And that spends phi, the work function, and then comes out. Now, depending upon what is your input energy, it will have EK max. So clearly, if you want to increase your EK max, what you have to do?
Increase the input energy.
Frequency, right?
Yeah.
This is constant. Phi is constant for a given surface.
Yeah.
Agreed? So now tell me if your EK max is 0. Where was EK max 0? Where do you think was
EK
EK max 0?
when the input was E0.
So therefore, then you will have that frequency is called as critical frequency. You have to, the minimum energy required or the minimum frequency required is called as threshold frequency or critical frequency. So therefore,
Okay.
how does this formula become? H F naught is equal to phi because EK max becomes 0.
Okay. And it's called, does it matter if you say critical or threshold? Or is it the same?
Called what?
Does it matter if you say critical frequency or threshold frequency, or are they the same?
No, they are the same. They are the same, but I
Okay.
think your book says critical. That's why I'm using this word. Otherwise, threshold is good word.
Okay.
Threshold is the minimum. Now there's another term that we have to put in. You just use the word work function. This is the first term that you have used. Second term that you're going to use is EK max, you already know, right? Because this is important, okay?
Yeah.
Third is critical frequency or threshold frequency, okay?
Okay.
At so critical or also called as threshold frequency. It is this, correct?
Yeah.
It is related to work function. You can calculate your work function by just, if you know HF naught, F naught, okay? So how do you define critical frequency?
The minimal frequency for the input energy in order to start the photoelectric effect.
Yes, very good. Needed to tracking. I hope you're writing now.
Yeah.
So minimum frequency required to start. Only to start, photoelectric effect. Clear?
Yeah.
Okay. Now let's take that equation again, because more than anything, the graphs are important, how you relate the graphs. Okay. So I can write the equation as HF input energy, HF. Wait a minute. I think the eraser is working better than the pen. Okay. So HF is equal to, what is that? Phi. Can I not write HF naught instead of phi? Correct?
Yeah. Yeah.
Plus EK max can also be written as half mv max squares. Please note, EK max can also be written as half mv max square. Clear?
Okay.
Okay, so I can keep this as it is EK max, because my graph will be with respect to this. Okay, does it not look like, okay, maybe I can rearrange this, because we are interested in graphs like, this. X-axis is the frequency, y-axis is the EK max. Please note EK max, it's not EK, okay? So your formula, you want to write this as y is equal to mx plus c, right? Because this is more like a straight line. We'll see this very soon. So EK max can be written as, I'll rearrange, EK max y is equal to mx plus c. X is f, right? So,
Yeah.
right, mx plus c can be, h f naught plus h f. Y is equal to mx plus c. Okay, let's write it. Y is equal to, where is x is f, right? So this part is x. And this is what? What is this?
The Planck's constant. Oh, yeah.
Gradient, and c. So can you relate, or please explain what I have done and how will the graph look like?
Okay. So what you did was you related the what you're trying to depict on the graph to the
Graph is,
equation for linear graph. Where EK max is gonna be on the y-axis and F is gonna be on the x-axis. And then what graph's gonna look like?
gradient is h.
Yeah, gradient is h, and then
It's a straight line with y-intercept c.
Yeah.
Okay. So, but then EK max, don't you think this is minus? See, this comes this side, so it's minus. Yes or no?
I'm not sure I get that entirely.
See, rearranges.
Why?
I have taken HF naught on the other side.
Yeah. Okay, yeah.
So that means your y-axis, when your y-intercept is negative, when x goes to 0. Okay. So that means
Yeah.
when frequency goes to 0,